Hello and welcome to our webinar Load Spectra and the FVA Workbench. My name is Christine Rabe. On the right side of your screen, you will see the control panel. Here you have the possibility to ask questions during the webinar via the question tab, and the questions will be answered after the webinar. In the tab Documents, we have provided an information flyer for you to download. After the webinar, you will receive a short questionnaire, and we would be pleased if you could take a few moments to complete it. I wish you a successful webinar and pass on to our speaker, Dr. Keuthen.
Thank you. Hello and welcome everybody from sunny Munich. My name is Moritz Keuthen. I'm the head of modeling and simulation at FVA. And in today's web seminar, I will demonstrate some of the capabilities of the FVA Workbench in regard to the calculation consideration of load spectra in your gearbox analysis. But before we go into details here, for those of you who are perhaps not that familiar with the FVA, a very short introduction. The FVA is a leading research and innovation network for drive technology, joining the expert community, the leading industry in this field with top universities, and in the more than 50 years of successful joint research, a lot of knowledge was generated, but as is the norm with research, sometimes it's difficult to transfer the latest findings into the daily work of the engineers, and to enable this transfer to improve the speed of usability. The FVA software and service was founded some years ago, which plays a crucial part in this network. Our range of services includes primarily the software, the simulation software FVA Workbench we're going to talk about today, but we also offer some soft services, I would say. We offer design and calculation services. We can set you up with leading experts in the field for specialist trainings, and we also organize conferences where you may share your latest findings and network. With that short introduction, let me come to today's agenda. We will touch on several aspects of service life calculation under the consideration of load spectra in the FVA Workbench. So for various machine elements, we won't go into much detail regarding each of those calculation methods. I assume you're familiar with them if you're interested in them, and focus more on the handling and where can you activate the calculation, what results can you get, and so on. If you have detailed technical questions regarding a special calculation, then we are always welcome to post them on our software support portal, and we'll endeavor to answer your questions in detail. So today we will start with cylindrical gears and service life according to the ISO 6336. We'll then move on to accumulated roller bearing life and service life of shaft notches according to the FKM guideline. We'll do a brief excursion into the topic of noise excitation and the possibilities you have here to consider varying loads via the load spectrum. We'll look at a model from a manual transmission of an automobile and see how you can specify load spectra for multiple gears and what results you get there. We look at example which includes bevel gears and possibilities to do service life calculation in this field. And in the end, I will demonstrate some of the possibilities the FVA Workbench supports you in extracting, I would say, calculatable load spectrum from real-world measurements. So without further ado, let me switch to to our workbench. I won't do an introduction into the basic handling of the workbench. If you are interested in that, I would recommend you some of the recorded web seminars on our homepage, which some of them touch onto general handling and modeling in the workbench, and some also go into more details regarding certain topics. For today's first example, I have chosen an industrial gearbox with 2 stages. Let's have a quick look at it. So 2 cylindrical stages, and if we have a more detailed look, then we see that it is a bit more interesting by a shaft and shaft bearing here between the input and the output shaft. And this will be our example model for our first calculations. And we start with the calculation according to ISO. Of course, usually a standard calculation for one operating point is performed. But if you want to do a load spectrum calculation, you may activate this here in our calculation overview control panel on the gear unit. And for those of you who are used to older versions of the workbench, then you may also specify directly here the load spectrum which is to be used. I think since the workbench 6, we moved the specification of the load spectrum here to the power flow tab, since in the case of multiple gears, we want to specify a load spectrum for each of those gears. For this simpler model, we have just 1 gear, and so we have here one load spectrum in our local database, which we want to consider for the moment. Also in the power flow is the input of the nominal power flow data, so the nominal rotational speeds and the nominal torque, respectively power, which is applied to the gearbox. And the load spectrum we specify here now acts on this nominal power flow. So for each of the load cases in the spectrum, you may specify a factor of the scaling factor for the torque, and if you are interested, you may also specify a scaling factor for the rotational speed. But for the moment, we just stick with the scaling of the torque. And you input here the frequency or the time share of each of those load cases in the total load spectrum. You may input this here as a percentage or as a factor or as some other value. In the end, this is relativized. So the time share of one of the load cases in the load spectrum is it's this number divided by the sum of all the time shares, and this is then multiplied total operating time of your gearbox to get the operating time for each of the load cases. So with that, let us start a first calculation to show some results. Yeah, I'll show you in a minute. Let me first talk to you while the calculation is running. We have some 160 calculation steps to perform here, so a few seconds to cover. The basic principle is that first we do a system calculation for various load cases in the load spectrum. So we apply the scaled torque. We solve the mechanical system, we look at shaft deflections, bearing stiffnesses, and the effects on the load distribution of the gears and so on. And we save all those results and then use them to do the calculations, service life calculations like the ISO here. You may specify the number of operating points for which the total system is calculated here in the control panel. So in this example, I selected 8 equally distributed calculations of the mechanical system, and for the remaining 25 or 25 minus 8 load cases, the relevant values like the load distribution for the cylindrical gears are interpolated between those more detailed results where we have a complete system calculation available. Of course, you may also calculate the complete system for each of the load cases in the load spectrum to get the most exact results, but this takes, of course, then a longer time than if you solve only a reasonable number of system calculations. We have now, the calculation is completed. We have the result here as a current snapshot in our report manager on the left bottom side. And we select the report template. I've prepared especially a template for today, but also the default templates already offer some of the results in this calculation. Let's look at the results. First of all is the gear unit, where we have an overview table of the safety factors according to the ISO for each of the gears. And as you can see, for the pitting and bending safety for the left flank and the right flank, as well as the static safeties. And in this case, at one stage the left flank is loaded, and the other the right flank is loaded. This explains those results, whereas of course for the unloaded flank we don't have the safety. In the case of the manual transmission, we look at it later. This is a more complex and more interesting table. And let's look at the single gears from a more detailed view. Of course, here's also some information on the geometry of the gear, on the tool used to manufacture it, on the modifications we applied. But what I want to talk about today are those diagrams here, which show the calculated pressure or stress spectrum for each of the gear flanks, or the left gear flank. And this is for the pitting, and this is for the bending strength. In green, you see the calculated load spectrum. In red, you see the maximum permissible load spectrum, which corresponds to a minus sum of 1. The scaling factor here is the corresponding safety factor. In addition, the static safety, so the scaling between here and here, is shown, and the damage the calculated load spectrum already generates is reported. In this case, most of the load spectrum is below the long life region of the SN curve, so we don't have a damage and a larger safety factor here. This is the left flank, of course, for the gears which are loaded on the right flank. Then we have the right flank spectrum. And if you have gears which are loaded left and right flank, or multiple meshes, then these results are combined. So this is a first view onto the results. Let's switch back to the model. And I we'll come back to the ISO with the manual transmission model. For the moment, let us continue to the next machine elements. We have several bearings here, which are of course of interest, and also some shaft notches. So let us activate the load capacity according to the FKM guideline for the shafts and the bearing lifetime calculation. There's a few more calculation steps, so this takes a bit longer. It gives me the opportunity to talk a bit about this. For the bearing, the same idea applies as we just talked about for the cylindrical gears. So first we do several system solves where we determine the corresponding nonlinear bearing stiffness, the resulting bearing loads. We save them, and afterwards, for each of the load cases in the specified load spectrum, we determine the interpolated bearing load from the calculated system solves, and we do a lifetime calculation. And in the end, we accumulate all those lifetimes for the different load cases into the accumulated lifetime. If you're looking at the shaft safety, here you have the possibility to calculate according to the FKM guideline. This offers you the possibility to get one combined safety factor for the different loadings of the shaft, whereas the DIN 743 just offers you safety factors for the bending and for the gradual load and so on, without the possibility to combine them into a single safety factor. So this is the reason why we only offer the FKM as a load spectrum calculation for the shaft safety. So we are currently working on improving the performance of the bearing calculations. And so if you have a look at our upcoming release in autumn, here we did some work on parallelizing and also improving the calculation speed of each of those calculations. So this will be a bit quicker than it is at the moment, but still we're doing almost 1,000 calculation steps here. But this is already pretty quick, in my opinion. As my colleague said already, you're welcome to pose questions during the talk or afterwards. Probably I will come to answering them afterwards, if we still have the time for it. I'm optimistic. So almost done now. And we have a new result. I won't go into much details regarding this calculation, so we won't look at each bearing separately. Just have a look at this overview tables here. So in our model, we have several tapered roller bearings from SKF. So besides the rating life according to the ISO 281, we also can calculate the rating life according to the SKF catalogs. Furthermore, we have a deep groove ball bearing from Schaeffler. For this, of course, we have the corresponding accumulated rating life according to the Schaeffler catalog. And finally, we have two needle rollers here, which are from the FVA manufacturer. Of course, there's no such manufacturer. This is a result of an FVA project some years ago, which took a bunch of catalog bearings and estimated some interior geometry parameters for them. And this database is available as an FVA manufacturer. So for these bearings, we have interior geometry data available and can also do the extended modified reference life rating calculations. Regarding the shaft safeties, we also get some overview here of the nominal cyclic safety factor of all loads combined. So this is really where the load spectrum goes into the calculation. In addition, of course, we also have a nominal static safety factor of all loads combined. And if we move to a shaft, of course, a lot of additional results regarding the FKM calculation are available. And of course, also for the bearings, much more information is available. But due to time limitations, I won't go into details here. I just wanted to show you what's possible and where you can find the results. So with that, we come back to the cylindrical gears and another type of analysis, the gear force excitation can also be calculated with the FVA-Workbench, and especially for excitation, it might be interesting to look at these results across varying loads. And this is also done using the load spectrum. So now for each of the 8 operating points we specified here from the load spectrum, again, the system calculation is performed, and afterwards the local tooth contact analysis and gear force excitation calculation. For this, I wanted to use a compact report, which is in your standard FVA-Workbench installation, available as overview report, which just focuses on the cylindrical stages. It also contains a lot of results. We just briefly look over them. We here have the 3D load distribution. We have a nice crowning and face width direction, but so far no profile modification. So of course we have load peaks at the beginning and the end of the mesh. And if we go down here, we see the transmission error across the load. So for the varying torques we applied here, and based on the transmission error, then results like the tooth force level and the force amplitudes are also calculated. And what we can see here, of course, is that with increasing torque, the transmission error increases, and also those other excitation parameters. So, of course, the more torque, the louder your gearbox. We already have a reduction here in the load torque regime, which would not be there if we didn't have the modifications along the face width. And we now want to look at what happens when we add also a profile modification. So let's get back to the model. Below the cylindrical gear, you find the modifications. We specified here a crowning, also a helix angle modification to compensate the shaft deflections at nominal load. And we now add a simple symmetric profile crowning for each of the stages. So here it's the same. We have a helix angle modification and crowning across the facet. And we now add also a profile crowning. And calculate again. And we'll look at the reports and comparison for some manual optimization. This is a really nice feature if you quickly want to look at what happens or do a bit of tuning. Of course, if you want to do a real full optimization or have lots of models where you want to do this kind of stuff, then I would recommend you some optimization in this procedure. The FVA Workbench offers a lot in this regard, scripting, or also automation plans. I think my colleague Markus Bisans talked a bit about this in the last web seminar. So if you're interested, have a look at our homepage. So we set the last calculation or the previous calculation as a reference, the current calculation as a comparison, and then we get a 2-column result report. On the right-hand side, we have the reference. Perhaps we have here some better names so that we know where we are. This was without profile modification, and this is with profile crowning. And so again, so here without profile modification on the left, with profile crowning, we immediately see the effect here on the 3D load distribution, which looks much nicer now. And we wanted to see what happens regarding our excitation parameters, and especially if you take into account the scaling of the y-axis, the horizontal axis, then you see that we just with a simple profile crowning already obtained nice results. We reduced the transmission error, especially in the region of the nominal torque, but also for a higher torque regime, which is covered in our load spectrum, we obtain better results than without the profile crowning. And of course, the same holds then for the other corresponding parameters. And yeah, as is usual, especially if you're looking at excitations, or more or less in general, of course, the modification is always optimal for one load. And if you have an application where you have to cover varying loads, then you have to find a compromise which offers the best overall performance. With that, I want to already finish our excursion into noise excitation for the cylindrical gears. Let me recommend you also a web seminar by my colleague Dennis Tazier, who spent a whole hour talking about the capabilities of the workbench in this regard and what you can do there. And yeah, with that, let's move on to a new model, which is the manual transmission from an automobile. We have here. We have a look at the power flow for this model. We have in total 7 gears, so 6 forward gears and 1 reverse gear. And you can now see here the switch matrix, where you can specify for each of the couplings in your model whether it's active or deactivated in each of the gears. And also you can specify the same for the loads. And in addition, you can now specify for each of the gears load spectrum from the, again, from the local database pool. Perhaps few words to the local database pool or where the results come from. Of course, you can directly edit your load spectrum here in the editor. Usually, or in general, you can add those results from the global database, where you can, so if you have some load spectra you use very often, you can just save them in your global database and reuse them. And it also offers a lot of capabilities regarding those load spectra. I will talk about this a bit later in the talk. So going back to our model, we specify a load spectrum for each of the gears. And in addition, we now specify a time share which is spent in this gear. So if you're interested in knowing for a specific load case in one of the gears, how much operating time does it get? You have, again, here the total operating time of the gearbox. Then the relative time share of the gear is determined by taking this number divided by the sum of all time shares. This is the then the operating time of this gear. And then the same logic applies with the last model. If you have the operating time for the gear or for this load spectrum, then again, the relative time share of one of the operating points in the spectrum is the relative time share is multiplied with the total time allocated for this load spectrum. Yes, I did this calculation in advance. There's a few thousand calculation steps which are necessary here to calculate this for all gears and all stages. So let's just have a look at the results, which I saved here as a model snapshot. And for this, we go back to the load spectrum system report. And yeah, this now contains a lot more data because we have a lot of machine elements here which contain calculation results. And now this overview table, the safety factors is of course much larger. Again, for each of the stages, for both gears, we have the safety factors. And as we can see now as well, we have several gears which are loaded on the left and the right flank at some point in this total calculation. So we have safety factors for the left and the right flank, whereas others are only always loaded on one side. So let's have a look at one of those gears which are loaded on the left and right flank. And basically we get the same diagrams here, again, as we saw already for the simpler model. Yes. If you are interested, especially in the question, how does this, or where does the damage in this load spectrum come from, then this here has a larger damage. We can also zoom out a bit and we see this more clearly. So this is mostly in the limited life range at the moment. We have a safety factor just above 1 and a total damage of 0.457. And I added an overview of the damage per gear for the left and right flank, bending and pitting. And here this is the pitting on the right flank. If we have a look here in this last row, then we can see that this damage comes from the 7th gear, which is the reverse gear. So this is the critical gear for this safety factor of this damage. If we have a look, I think that one is actually a bit overloaded by this given load spectrum. So the calculated load spectrum is well above the SN curve already. Accordingly, we have a safety factor of below 1 and a total damage of almost 8. And yeah, if we have a look again here, this is the right flank for pitting, then we see that most of the damage occurs in the first gear, but also a sizable amount, too large amount in the reverse gear, where this gear is loaded on the right flank, whereas the left flank load is still okay. So that's what I wanted to show you in a quick overview regarding the specification of load spectra for multiple years. And we'll move on to our next example model. This is again an industrial gearbox example, which now also includes a bevel stage. And we now want to look at the local tooth contact analysis of this bevel stage in the context of varying loads. And yeah, let's first do a quick system calculation. So how does the system affect this bevel stage? Well, of course, the shaft deflections and the bearing stiffness and so on all combine in certain deformations and deflections, and which lead to shift in the relative position. Of course, this is very much exaggerated here, of the pinion to the wheel, and thus affect the local load distribution and all later calculation results. And yeah, of course, these deflection differ for varying torques in the system. So if we want to consider them in our analysis, we should activate again the load spectrum calculation. In this case, yeah, our load spectrum is not the largest one. It offers a scaling of speed and torque. And for each of them, we do the system calculation. And afterwards, we want to do a local damage accumulation, considering this load spectrum for the bevel gear. Of course, we could also add a couple of other calculations for the cylindrical gears, for the bearings, for the shafts. But for the sake of this demonstration, we'll just focus on the bevel stage. For this, I select another report template, which just focuses on the results of the bevel gears. And for this, we have a very nice overview of the accumulated damage for the tooth root and the pitting safety calculations for the pinion and the wheel. So for the tooth root, you get values across the face width, for the pitting, you get values for over the whole flank, which you can use to really look where's the problem in your model. The input for these calculations are shown here. So with increasing driver torque, various parameters which characterize the relative position between pinion and wheel increase. And we have a lot of nice overview results of the corresponding calculation results for each of the loads. So we have here the maximum head pressure for each of the load cases, the maximum tooth root stresses, also other like the efficiency, noise and excitation, safety against scuffing, and so on. So you can really dig deep into what happens with your bevel stage for your load spectrum and which load case contributes where and to what. Yes, of course, this was now a local method which used local tooth contact analysis. Of course, you could also calculate simply according to the standard, the ISO 10300, considering a load spectrum or the bevel stage. So with that, let me move on to the question of where does the load spectrum come from? How do we get a load spectrum in this format when we have real-time measurements? And just to demonstrate some of the capabilities of the workbench in this regard, we start with the first one, which is call example 1. Of course, you could, if you already have the load spectrum in the right format, just paste it from your clipboard or do a CSV import or start to input the data here by hand. But what I want to show you today is behind this calculate button. And one of the possibilities we have here is to do a multiple parameter time at level counting. Eine mehrparametrische Verweildauerzählung from the German colleagues. And for this, we specify some files, speed and the torque. And just let me briefly show you how such a file looks like. It's just a 2-column text file where we have the second, so the timestamps and the corresponding values. So in this case, this is the torque file, and we have some 200,000 entries, measurement points in this file. And the same goes for the speed. We have to input the number of classes we want to obtain for each of those parameters. Let's say 10 classes for speed and torque. And then we can suggest the class lower and upper boundaries. And we have to input the nominal torque and speed to which this is relative. So I think in this case, this is about 500 Newton meter nominal torque and 1000 rotations per minute relative speed. And you, of course, also have some other options here, which I don't want to go into details. And takes a moment, and we obtain our corresponding load spectrum, which now has 50 load cases. And when we look at here, of course, this is a spectra. We see the different classes of the speed, and for each of them, the corresponding torques in which were classified. And we also have the same torque here again for different speeds, so that we have the 10 classes for each of the columns. And we now could use this to look again at our bevel stage, for example. Of course, if you start with real-world measurements, often you end up with very large load spectra, which are nice to look at if you really want to have a detailed look. But sometimes you just want to get a feeling where things are going, or you want to do some optimizations, and you don't need this detailedness or exactness. And you might want to look at reducing the size of this load spectrum without destroying all the information which is available there. And so we want to perhaps reduce the size of this load spectrum. And let me quickly demonstrate this. For this, we do a multiple column class reduction. We select the example we just looked at. So this ended up with 9 torque classes and 8 speed classes. Perhaps we just want to have 5 of each. Again, click at finish, and we get a reduced size of the load spectrum here, which allows us a quicker calculation. Final example. One problem with this time at level calculation is that it does not take into account a lot of information about the progress of your measurement. If you're an expert in this field, you may want to do more sophisticated rainflow classification of your load time series. For this, we specify the torque file we just looked at. This is in Newton meter, and we specify a number of classes to be 50. The upper and lower class boundaries were already calculated. And as a first step, corresponding rainflow matrix is generated from these measurements, so which classifies the measurements. And afterwards, we, if we want to consider this in our calculation, we need to do a so-called amplitude transformation of this rainflow matrix. Usually this is done for stress spectra, but if you know what you're doing, you may also use it for something like a torque spectrum. But yeah, you should be an expert, of course. Just to show you what's possible here, we do this now without thinking too much about it, and obtain the resulting load spectrum, which from the amplitude transformation of this rainflow matrix. So those were just some examples of the capabilities of the Workbench. There's a lot more here, so if you're interested in this, have a look, try it out, or if you have some questions, again, I recommend you to use our support system. You find it over the button Help, Contact Support System, direct link into our ticketing system, where we are glad to help you if the need arises. So with that, let me come back to my slides. A short preview to our upcoming release, the FVA Workbench 7.0 in autumn. One of the aspects we're working on there is the calculation of the overall gearbox efficiency. And this is then iteratively determined and considers the effects of the friction losses in the mechanical system. So, of course, those losses result in decreased loads and displacements along the power flow when compared to a nominal power flow without losses. And for the losses, also the varying speed might be interesting, of course. And in the 7.0, you may then fully combine the possibilities of the efficiency calculation and its results on the mechanical system with a load spectrum calculation, like we looked at today. So with this preview, let me summarize the points we talked about today. We started with looking at the service life of cylindrical gears according to the ISO 6336. We briefly looked at roller bearing life accumulation in the load spectrum, the service life of shaft notches according to the FKM guideline. We did a brief excursion into noise excitation of cylindrical gears. We looked at the specification of load spectra for gearbox with multiple gears for manual transmission. An automobile, we looked at bevel gears and calculation capabilities in this regard. And in the end, I demonstrated some of the possibilities where the Workbench helps you to extract a calculatable load spectrum from real-world measurements. Let me finish with pointing out some upcoming events. After the summer break, we have a live online seminar on gear damage and its influencing factors by the expert Klaus Michaelis from the Gear Research Center FZG in Munich. And in the second half of September, there's the eMotive online conference for electric mobility. If you're interested, have a look at our homepage. With that, I thank you very much for your interest, and if you have any questions right away, I'll be happy to try to answer them. Otherwise, of course, you may also post them in our support system and get a very detailed report there. Thank you very much.